Hello students, welcome to this new video on mechanical properties of solids part 2, which is given in section 9.5 to 9.7 of chapter number 9 of physics for class 11. As you all know, in the previous video, that is part 1, we studied about elastic behavior of solids, stress and strain, as well as Hooke's law. This is continuation of those previous sections. In this section, we will study about stress strain curve, elastic moduli, applications of elastic behavior of material. This is a simple topic. You have to just listen attentively and note down important points. Let us start. The relation between stress and strain for a given test material can be found by applying a tensile force or a compression force. In a standard test of tensile properties, a test cylinder or a wire is stretched by an applied force. That means the test material can be in the form of a cylinder or a stretched wire. The fractional change in length, that is the strength and the applied force needed to cause the strain are recorded. That is, the values of stress and strain are recorded. The applied force is gradually increased in steps and the change in length is noted. A graph is plotted between stress, which is equal in magnitude to the applied force per unit area. That is, the stress is the applied force divided by the unit area of the test material and the strain produced. So this is plotted, these figures are plotted in the graph as shown in the figure. O is the origin, OX, this is OX, x-axis, that is strain is plotted on the x-axis and stress is on the y-axis. OY is the vertical line, is the y-axis. And the graph thus obtained from the experimental results is marked as O, P, E, A, B and C. We will now study about each and every point on this graph. This graph is called stress strain curve. A typical graph for material is shown in the figure. The stress strain curves vary from material to material. That is, the graph is a unique property of the respective material. These curves help us to understand how a given material deforms with the increasing load. From the graph, we can see that in the region between O and P, the curve is linear. That is, between O and P, the curve is linear. In this region, Hooke's law is obtained. The body regains its original dimensions when the applied force is removed. Suppose if we remove the load from this, at this point, the body regains its original dimensions and hence the solid behaves as elastic body. So to the left of this vertical line red, that is point E in the graph, the region is elastic region, which is also written in the graph. In the region beyond E, that is E to A, stress and strain are not proportional. Here, the proportionality is not there. The stress is not proportional to strain. So, Hooke's law is not obeyed. The body still returns to its original dimension when load is removed. Point E is known as the yield point. Yield point or elastic limit. This is called elastic limit and the corresponding stress is designated as sigma y, which is yield strength. This is the yield strength of the material. If the load is increased further, the stress developed exceeds the yield strength. If you increase the load further beyond E, exceeds the E, the yield strength and strength increase rapidly and even for a small change in the stress. The portion of the curve between E and B shows this. That is, the stress increases rapidly. Stresses increase rapidly. In this the case, even when the stress is zero, the strain is not zero. The material is said to be permanently set. That is, the point A to the left is here at this point A. The material is said to be permanently set. The deformation is said to be plastic deformation. So the region towards the right is plastic region and to the left is elastic region. The point B on the graph is ultimate tensile strength. So here the stress corresponding to the point B, which is marked in the dotted lines and marked as sigma u, is the ultimate tensile strength. Ultimate strength sigma u. Beyond this point, the strain is produced even by a reduced applied force. The fracture occurs at point C. The fracture occurs at point C. Therefore, if the ultimate strength and fracture points B and C are close, the material is said to be brittle. The distance between B and C determines the type of material. If B and C are very close, then it is a brittle material. If B and C is large, then it is a ductile material. We will study about the brittle material and ductile material in the next slide. The stress strain curve for different materials is shown on the screen. As explained in the previous slide, the test materials were selected as a brittle material or ductile material or elastomers. Elastomers are nothing but rubber material. Figure A shows the graph, stress strain graph of brittle material. The plastic region, as explained in the previous slide, that is between E and C, is very small for a brittle material. This is the graph for brittle material. The distance between the plastic region between E and C is very small and it will break soon after the elastic limit is crossed. So brittle material break very easily. The graph for a ductile material is shown in figure B. That is, figure B shows the stress strain curve for a ductile material. The material of this type have a good plastic range. That is, the region between E and C is large and such materials can be easily changed into different shapes and can be drawn into thin wires. The third type of materials are elastomers. For elastomers, the strain produced is much larger than the stress applied and the graph is shown in figure C. Such materials have no plastic region range and the break point lies very close to the elastic limit. Example, rubber. Elastic moduli. The proportional region within the elastic limit of the stress strain curve, which we discussed in the previous slide, is of great importance for structural and manufacturing engineering designs. This graph is reproduced in this slide. We know that the Hooke's law, which stated that within the elastic limit, stress is proportional to the strain. That is, that can be written as, using mathematically, stress is proportional to strain, or stress by strain is equal to constant, that is equal to represented by the letter small k. This constant K is called modulus of elasticity. The value of modulus of elasticity depends on the nature of the material, that is, the characteristics of the material and the manner in which the body is deformed. Its value depends on the temperature of the body. Its value is independent of the dimensions of the body. There are three types of moduli of elasticity corresponding to three types of strain. Please note it depends on the type of strain. First one is Young's modulus, represented by symbol capital Y, and bulk modulus, represented by capital letter capital K, and shear modulus, also called modulus of rigidity, which is represented by letter capital G, and sometimes it is written and its symbol is eta. Young's modulus. Experimental observations show that for a given material, the magnitude of strain produced is same whether stress is tensile or compressive. The ratio of tensile or compressive stress, represented by the symbol sigma, to the longitudinal strain, represented by symbol epsilon, is defined as Young's modulus and is denoted by the symbol capital Y. Thus, Young's modulus is defined as the ratio of normal stress sigma to the longitudinal strain epsilon within the limit of proportionality. Please note limit of proportionality. Thus, it can also be mathematically written as capital Y is equal to normal stress divided by longitudinal strain, that is equal to sigma divided by epsilon, that is equal to sigma is nothing but F by A, force per unit area, F by A divided by delta L by L. Here delta L is the change in length and capital L is the original length. This ratio can be rearranged as F into L divided by A into delta L. The table shows the value of Young's moduli and yield strength of some selected material. From the data given in this table, it is noticed that metals Young's moduli are large. Therefore, these materials require a large force to produce small change in length. For example, to increase the length of a thin steel of wire of 0.1 cm square cross-sectional area by 0.1%, a force of 2000 newtons is required. The force required to produce the same strength in aluminium, brass and copper wires have the same cross-sectional area are 690 newtons, 900 newtons and 1100 newtons respectively. It means that steel is more elastic than copper, brass and aluminium. It is thus for this reason steel is used in heavy duty machines and in structural designs. Wood, bone and concrete and glass have rather smaller Young's modulus. Please pause it and go through it in detail. Determination of Young's modulus of a wire. A typical arrangement to determine the Young's modulus of a wire under tension is shown in the figure on the screen. It consists of two long straight wires A and B of same length and equal radius suspended side by side from a fixed rigid support. This is a fixed rigid support. The wire A is called reference wire, carries a millimeter main scale and a pan to place the weight. The wire B, which is called experimental wire of uniform area of cross section, also carries a pan in which known weights can be placed. A vernier scale V is attached at the bottom of the experimental wire B. The main scale M is fixed to the reference wire A, and the weight placed in the pan exert a downward force and set the experimental wire under tensile stress. The elongation of the wire, that is, the increase in length, is measured by vernier arrangement. The reference wire is used to compensate for any change in length that may occur due to change in room temperature, since the change in length of the reference wire due to temperature change will be accompanied by equal change in experimental wire. Thus, both the reference wire and experimental wires are given an initial small load to keep the wires straight, and vernier reading is noted. Now the experimental wire is gradually loaded with more weights to bring it under a tensile stress, and vernier reading is noted. The difference between two vernier readings gives the elongation produced in the wire. Let small r and capital L be the initial radius and length of the experimental wire respectively. Then the area of cross section of the wire is pi r square. Let capital M be the mass that is placed that produces an elongation delta L in the wire. Thus, the applied force is equal to M into G, where G is the acceleration due to gravity. The Young's modulus of the experimental wire is given by the relation as shown as discussed in the previous slide is Y is equal to capital Y is equal to sigma by epsilon. That is equal to capital M into G divided by pi r square. Capital M into G is the force and pi r square is the area into L by delta L. Let it be equation 1. Rearranging, we write Y is equal to M into G into L divided by pi r square into delta L. From this equation, we can determine the value of Young's modulus of the wire. Shear modulus. The ratio of shear stress to the corresponding shear strain is called the shear modulus of the material and is represented by capital G, letter capital G. It is also called the modulus of rigidity. Therefore, shear modulus capital G equals shear stress sigma S by shear strain epsilon. Therefore, that can be written as F by A, that is shear stress is force per unit area, divided by shear strain, that is change in length to original length. That is equal to F into L divided by A into delta X. That is equal to rearranging F divided by A and angle theta. It is written as F by A into theta. Shear stress sigma S can also be written as sigma S is equal to G into theta. The SI unit of shear modulus is newtons per meter square or Pascal. The shear moduli of common materials is shown in the figure. Please note down the difference between metals and other materials such as wood. The shear moduli of common materials are shown in the table 2. It can be seen that the shear modulus or modulus of rigidity is generally less than Young's modulus. Please compare table values in table 1 and table 2 and find out yourself that shear modulus G is less than Y. For most of the materials, G is far greater than Y by 3. Bulk modulus. We know that when a body is submerged in a fluid, it undergoes a hydraulic stress equal in magnitude to the hydraulic pressure. This leads to the decrease in the volume of the body, which produces a strain called volume strain, given by the relations delta V by capital V, where delta V is the change in volume and capital V is the original volume. The ratio of hydraulic stress to the corresponding hydraulic strain is called bulk modulus, which is represented by the symbol letter capital B. Thus, capital B, that is bulk modulus, is equal to minus of P divided by delta V by capital V, where the negative sign indicates that with an increase in pressure, there is a decrease in volume. That is, if pressure P is positive, del V is negative. If the system is in equilibrium, the value of bulk modulus is always positive. The SI unit of bulk modulus is same as that of pressure, that is newtons per meter square, that is newtons per meter square, or Pascal, that is PA. The bulk moduli of a few materials common are given in the table 3 shown in the next slide. The reciprocal of bulk modulus is called compressibility, and compressibility is denoted by letter small k. It is defined as the fractional change in volume per unit increase in pressure. Therefore, K is equal to small k is equal to, that is compressibility, K is equal to 1 over P, that is equal to minus of 1 over delta P into delta V by capital V. Here delta P is the fractional change in pressure. Gases are about a million times more compressible than solids. Gases have large compressibility which vary with pressure and temperature. Table 3 shows the bulk moduli B of common materials. Please see the table below, that is shown on the screen. The left side is the materials. The materials are classified as solids, number 2 liquids, and number 3 gases. So the solids have the bulk modulus of solids is far greater than bulk moduli of liquids and gases. Solids are least compressible. So please compare the materials aluminum, brass, copper, glass, iron, nickel and steel and their Bulk moduli. The bulk moduli of liquids is far greater than bulk moduli of gases, that is less than solids. Gases are most compressible. Among the liquid, water, ethanol, carbon disulfide and glycerin or mercury are shown in the table. For gases, air at standard temperature and pressure is 1 into 10 to the power of minus 4 newtons per meter square. Table 4 shows the various types of stress, strain, elastic moduli and the applicable state of matter at a glance. Column 1 shows the typical stress, that is tensile or compression or shearing or hydraulic. The stress is equal and opposite to the force, that is in case of tensile or compression stress, the stress is equal and opposite and perpendicular to the opposite faces. That is, you consider for example, the case of a cylinder. So vertically, both tensile and compression are applied on the cross section area at the top and the bottom, which are perpendicular to each other. The elongation in compression is delta L by L. Though no there is a change in shape but no change in volume, and Young's modulus is applied. In case of shearing forces, sigma S, the letter represented by the letter, shearing stress is sigma S, that is equal to F by A also, but here the forces are acting parallel to each other, and the top and the bottom is usually fixed. Therefore, the pure strain is theta, that is angular change. There is a change in shape but no change in volume. It gives the shear rigidity represented by capital G. The third case is that of a hydraulic. In case of a liquid, there is no change in shape but volume changes, and its modulus is bulk modulus V, given by the relation B is equal to minus P by delta V by V. This can also be applied for solid, liquid and gases, whereas tensile or compression or shear stresses are applied only to solids. Poisson's ratio. A careful observations with the Young's modulus experiments discussed in the previous slides show that there is also a slight reduction in cross-section area of the wire. That is, there is a decrease in the diameter of the wire. Thus, Poisson's ratio takes into account the changes in length as well as the cross-section area. Here, to understand Poisson's ratio, we will define lateral strain. The ratio of change in radius to the original radius is called the lateral strain. Longitudinal strain. The ratio of change in length, please underline change in length to the original length, is called the longitudinal strain. Hence, the ratio of lateral strain to the longitudinal strain is called Poisson's ratio, and it is represented by the letter sigma. Sigma is equal to lateral strain by longitudinal strain. If the original diameter of the wire is small d and the contraction in diameter under stress is delta d, the lateral strain is delta D by D, that is change in diameter to the original diameter. If the original length of wire is L, capital L, and elongation under stress is delta L, the longitudinal strain is delta L by L. Please note that here sometimes we are expressing changes in diameter or changes in radius. Because it is a ratio, it is immaterial. The ratio remains the same. Therefore, the Poisson's ratio is then defined by delta D by small d divided by delta L by capital L, or delta D by delta L into capital L by small d. Therefore, Poisson's ratio is a ratio of two strains. It is a pure number and has no dimensions or units. Its value depends only on the nature of the material, or it is the characteristics of the material. For steel, the value of Poisson's ratio is between 0.28 and 0.30, and for aluminum alloys, it is about 0.33. Now we will proceed to derive an expression for elastic potential energy of a stretched wire. When a wire is put under tensile stress, the work is done against the interatomic forces. This work is stored in the wire in the form of elastic potential energy. When a wire of original length capital L and cross section area capital A is subjected to a deforming force F along the length of the wire, then let the change of wire be that small l. So original length was capital L, change in length is small l. And then we have F is equal to YA into small l by capital L. This is small l. This numerator is small l by capital L. Here Y is the Young's modulus of the material of the wire. Now for further elongation of a small change, infinitesimal small chain length del dl, the work done is dw. Change in work done is dw is F into dl or YA LdL by capital L. Therefore, the amount of work done W in increasing the length from original length capital L to capital L plus small l is given by the integral formula. W is equal to integral 0 to L, that is integral 0 to L of YAL divided by capital L into of dl. Here Y is the Young's modulus, A is the area, small l is the change in length or elongation, capital L is the original length, and dl is the differential. Therefore, W is equal to YA by 2 integrating, that is LdL is L square by 2. Therefore, integral of LdL is L square by 2. And from the knowledge of integration, we get W is equal to YA divided by 2 into L square by capital L. That is equal to, given by W is equal to half of Y into L by L of whole square into capital A into L. Therefore, W is equal to half of Y is Young's modulus, L by L is strain square into A into L is the volume of the wire. Therefore, W is equal to half of stress into strain into volume of the wire. This work is stored in the wire in the form of elastic potential energy represented by letter capital U, and it is therefore the elastic potential energy per unit volume. That is, if we divide W by V unit volume, we get the value of U. Therefore, U is given by U is equal to sigma into epsilon. Applications of elastic behavior of materials. The elastic behavior of materials play an important role in everyday life. All engineering designs require precise knowledge of the elastic behavior of materials. For example, while designing a building, the structural design of columns, beams, and supports require knowledge of strength materials used. The figure below shows different forms of the bars and pillars that are used in design of buildings. The first one is a bar with thickness B and length D. These are designed using the knowledge of elastic behavior of materials. The second one is buckling of a thin bar, which is also determined the design aspects of the building. The third is an I section used for designing a load bearing bar which has got flat ends at the top and the bottom. The third one is a pillar with distributed ends. The engineers select the applicable formations and applicable design using the elastic knowledge of elastic behavior of material. Thus, the first application of elastic behavior of materials is design of buildings, the structural design of columns, beams used in construction of bridges and multi-storied buildings. The second use is to determine the thickness of metallic rope used in the crane. That is also calculated using the knowledge of elasticity. And the third one is to estimate the maximum height of a mountain on the earth. A worked example is also done in the subsequent slide of this video. The fourth example is design of a hollow shaft which is much more stronger than a solid shaft made of same mass, length and material. This is also done using the knowledge of elastic behavior of materials. Now, having the basic knowledge of all the elastic behavior of materials, we will work out some examples. Question number 1. A structural steel rod has a radius of 10 mm and a length of 1 meter. A 100 kN force stretches it along its length. Calculate the stress, elongation and strain on the rod. Young's modulus of the structure of steel is assumed as 2.0 into 10 to the power of 11 newtons per meter square. Answer. We know that stress is equal to force per unit area. That is, stress is equal to F by A, and that is equal to F by pi r square, because the radius is given and pi r square is the area of the steel rod. Therefore, substituting the values, it is given 100 kilonewtons, which is 100 into 10 to the power of 3, divided pi is 3.14 into r is, the radius is 10 mm, that is 10 to the power of minus 2, r square is 10 to the power of minus 2 whole square, that is calculating, we get the value as 3.18 into 10 to the power of 8 newtons per meter square. The elongation is given by delta L is equal to F by L into capital L divided by Y, where F is the delta L is the change in length and F is the applied force, L is the original length of the rod and Y is the Young's modulus. Therefore, we have calculated F by A, that is 3 into 1.8 into 10 to the power of 8 and length is 1 meter, divided by 2.0 into 10 to the power of 11. That is equal to 1.59 into 10 to the power of minus 3 meters. So that is 1.59 millimeter. Therefore, the strength is given by change in length over original length, that is delta L by L. That is equal to 1.59, we have calculated previously, 1.59 millimeter, 1.59 into 10 to the power minus 3 divided by 1. 1 meter is the length of the rod. Therefore, that is 0.16%. Next question. Question number 2. A copper wire of length 2.2 meters and a steel wire of length 1.6 meters, both diameter 3 millimeter, are connected end to end. When they stretched by a load, the net elongation is found to be 0.7 millimeter. Obtain the load applied. Given Yc is equal to copper wire, that is Young's modulus of copper wire is 1.1 into 10 to the power of 11 Newton per meter square, and Young's modulus of steel is 2 into 10 to the power of 11 newtons per meter square. Answer. Young's modulus is given by the relation Y is equal to stress by strain, that is equal to W by A divided by delta L by L. Therefore, that is equal to W by A is equal to Yc into del of Lc divided by capital Lc. That is equal to Ys into del Ls by capital Ls. So, therefore, del Ic by del S, that is dividing one the both the relations, we get Ys by Yc into Lc by Ls is equal to, substituting the values, we get the answer as del Ic by del Is is equal to 2.5. Therefore, given the total elongation, delta C plus delta Ls is equal to 7.0 into 10 to the power of minus 4 meter. That is delta Lc is equal to 2.5 into delta Ls. That is equal to 5 into 10 to the power of minus 4 meter. Therefore, delta Ls is equal to 2.0 into 10 to the power of minus 4. Therefore, W is equal to A into Yc into delta Lc divided by Lc. That is, substituting the values, we get W as 1.8 into 10 to the power of 2 newtons. That is the answer. Question 3, that is third work example. In a human pyramid of a circus, the entire weight of the balanced group is supported by the legs of a performer who is lying on his back as shown in the figure. The combined mass of all persons performing the act and the tables, plates, etc. involved is 280 kgs. The mass of the performer lying on his back at the bottom of the pyramid is 60 kgs. Each thigh bone, femur, of this performer has a length of 50 centimeters and effective radius of 2 centimeters. Determine the amount by which each thigh bone gets compressed under the extra load. Given Young's modulus of thigh bone equals 9.4 into 10 to the power of 9 newtons per meter square. Please read the question again and note down all the given parameters. Let us answer the question. The total mass is equal to 280 kgs. Mass of the performer is given as 60 kgs. Mass of supported by the performer is equal to 280 minus 60 kgs. That is equal to 220 kgs. Weight, that is the weight, calculating weight equals m into g, that is 220 into 9.8 newtons, 220 into 9.8 newtons, that is equal to 2156 newtons. Weight supported by thigh bone is 2156 divided by 2, because there are two thighs and each one supports 1078 newtons. Given length of thigh bone is 50 centimeter, that is equal to 0.5 meter, and radius is 2 centimeters. Cross section area of the thigh bone A is equal to pi into r square, that is 3.14 into 2 into 10 to the power of minus 2 whole square meter square, that is pi r square. Simplifying, we get 1.26 into 10 to the power of minus 3 meter square. That is the cross section area of the thigh bone. Therefore, using the formula, delta L is equal to F into capital L divided by Y into A. Substituting the values, we get delta L is equal to the fractional decrease, delta L by L is equal to 0.00, that is 0.000091 or 0.0091 percentage. Please you calculate, simplify this using the calculator. Next work example, question number 4. A square lead slab of side 50 centimeters and thickness centimeter is subjected to a shearing force on its narrow face of 9 into 10 to the power of 4 newtons. The lower edge is riveted to the floor, that is, it is fixed. How much will the upper edge be displaced? Take the value of G equals capital G is equal to 5.6 into 10 to the power of 9 newtons per meter square for lead. That is, G is the shear modulus. Therefore, the lead slab is fixed and the force applied parallel to the narrow face as shown in the figure. That is, the force is applied as shown. F is the applied force at the top. The bottom edge is fixed and the length is 50 centimeters. Side, a square slab, and 50 centimeters. Therefore, the area of the face parallel to which force is applied is 50 into 10. So this is 10 centimeters and this is 50 centimeters. So A is equal to 50 centimeter into 10 centimeter. That is equal to 0.5 meter into 0.1 meters. So that is converting centimeter into meter. Both 50 is 0.5 and 10 centimeter is 0.1 meter. That is equal to 0.05 meter square. Therefore, stress applied is force per unit area, that is equal to 9.4 into 10 to the power of 4, that is the given force, divided by 0.05 meter square. Therefore, that value comes to simplify it into 1.8 into 10 to the power of 6 Newton meters per meter square. Therefore, by definition, shearing strain is equal to delta x by L, that is equal to stress divided by G. Therefore, displacement is given by delta x is equal to L into stress by G. So, knowing the value of L, stress, and given value of G, we can calculate the displacement. Substituting the values, we get the answer as 0.16 millimeter. A similar question is asked in subsequent slide, wherein we have to conduct an experiment and determine the value of G. By measuring delta x, actually we can find the value of G, which we will take up in the questions and answer session. Question number 5. The average depth of the Indian Ocean is about 3000 meters. Calculate the fractional compression delta V by V of water at the bottom of the ocean, given that bulk modulus of water is 2.2 into 10 to the power of 9 newtons per meter square. Take the value of g, small g, that is acceleration due to gravity, as 10 meters per second square. Answer. The pressure exerted by 3000 meters of column of water on the bottom layer is P is equal to H into rho into G, where P is the pressure, H is the height, rho is the density of water, and G is the acceleration due to gravity. Substituting the values, we get the value of P as 3 into 10 to the power of 7 kgs per meter per second square. That is equal to 3 into 10 to the power of 7 newtons per meter square. Fractional compression is given by delta V by V, where delta V is the change in volume and V is the original volume. That is equal to stress divided by V, and hence we can substitute the values which we have calculated for P is divided by V is 2.2 into 10 to the power of 9 newtons per meter square. So that we can find the value as 1.36 percentage. You please pause this video and do the calculations in detail. Next questions, we will take up very short answer questions quickly. These are questions of 1 mark. Why do the spring balances show wrong readings after a prolonged use? That is, they have been used for a long time. This is due to elastic fatigue. Question number 2. Why do we prefer steel to copper in manufacture of spring? Because steel is more elastic than copper, as its Young's modulus is more than that of copper. Draw the strain curve for elastomers. Answer. The stress strain curve of elastomers is shown in the figure. So it is bent. This curve can be bent inside or outside, in the other way also. In some of the books it is shown as pointing upwards, curve pointing upwards. How are we able to break a wire? By repeated bending. Repeated bending of wire decreases elastic strength and therefore it can be broken easily. Question number 5. What is the value of bulk modulus of an incompressible liquid? Bulk modulus is given by the relation stress by strain. K is equal to stress by strain, that is, stress is equal to incompressible, strain is 0. Therefore, the denominator is 0 and K, the value of bulk modulus K equals infinity. Define Poisson's ratio. Does it have any unit? Poisson's ratio is a ratio of lateral strain to longitudinal strain. It has no units. What is the elastic fatigue? It is the loss in strength of the material caused due to repeated alternating strains to which material is subjected. Question number 8. Why is it easier to swim in sea water than in river water? The density of sea water is more than the density of river water. Hence, sea water gives more upthrust for the same volume of water. This question number 8, you please skip for the time being. This we will study in detail in the next chapter, that is chapter number 10. Railway tracks are laid on large size wooden sleepers. Why? This is spread this spreads the force due to weight of the train on the larger area and hence reduces the pressure considerably and in turn prevents yielding of the ground under the weight of the train. Next question, question number 10. The dams of water reservoir are made thick near the bottom. Why? Answer. The pressure exerted by the liquid column is HPG, where H is the height, P is the pressure, and G is the acceleration due to gravity. So as H increases, P increases. So this pressure is given by P is equal to H rho into G. So as H increases, P also increases. So to withstand the high pressure, dams are made thick at the bottom. Short answer questions of 2 marks each. Question number 11. State Hooke's law. Deduce expression for Young's modulus of material of a wire of length L, radius cross section R, loaded with a body of mass M, producing an extension delta L in it. This is a theoretical question already we have worked out. However, the answer is repeated. You can pause and note down the contents and make your own notes. Question number 12. A wire of length L and area of cross section A and Young's modulus Y is stretched by an amount X. What is the work done? So work done also example we have done it, and the answer is repeated. You can copy down, pause and copy down. Next we will take question number 13. Prove that the elastic potential energy per unit volume is equal to stress and into strain. So this is also we have worked, this is also a worked example in theory part, and the explanation is also given. However, the answer you can pause and note down in this video. Question number 14. Define the term bulk modulus. Give its SI unit. Give the relation between bulk modulus and compressibility. The ratio of hydraulic stress to corresponding hydraulic strain is called bulk modulus. It is denoted by symbol capital P, that is equal to minus of P by delta V by V, where B is the bulk modulus, P is the pressure, and delta V is the change in volume and V is the volume. SI unit of bulk modulus is newtons per meter square or Pascal. The reciprocal of bulk modulus is called compressibility and is denoted by the letter small k. It is defined as the fractional change in volume per unit increase in pressure. Hence, small k is equal to 1 over B, that is equal to minus of 1 over delta P into delta V by V. We'll continue with short answer questions of second mark. Define the shear modulus with the help of a diagram and explain how shear modulus can be calculated. Answer. Definition. The ratio of shearing stress to the corresponding shearing strain is called shear modulus of the material and is represented by letter capital G. It is also called the modulus of rigidity. The diagram to calculate the shear modulus is shown below, shown on the screen. The first method is by measuring the dimensions of the sample material. This is explained already in our work example, that is in question number 3. Here, by measuring the delta L or the angle theta, we can determine the value of the capital G. In that problem we had assumed the value of G. Here we have to calculate the value of G. The shear modulus can also be calculated from stress and strain graph as shown in figure on the right hand side. That is in this figure. Within the elastic limit or linear limit, we have to select 2 points x1 and p1 and p2, and determine and note down its coordinate as epsilon 1 and sigma 1. And this for point P2, it is epsilon 2 and sigma 2. And we can calculate the value of G using the formula. Please note strain is on the x-axis and stress is on the y-axis. Hence, the coordinates are epsilon 2 and sigma 2 or epsilon 1 or sigma 1. Therefore, using the formula, G is equal to shear stress sigma s divided by shear strain epsilon s. That is equal to, we can find using graphical method, that is stress versus strain curve. That is, the slope is given by sigma 1 minus sigma 2 divided by epsilon 1 minus epsilon 2, that is equal to G. There is yet another method using relations between elastic constant, which is given by the formula y is equal to 2G into 1 plus sigma, where this sigma is Poisson's ratio and B is the bulk modulus and Y is the Young's modulus. Question number 16. Which is more elastic, steel or rubber? Answer. The Young's modulus Y is given by F by A is equal to delta L by L, and similarly we can calculate the Young's modulus for both steel and rubber, and simplifying we find Young's modulus of steel to Young's modulus of R rubber equals given by change in length of rubber to change in length of steel. Hence that is greater than 1 because the rubber is more stretchable and delta R is always greater than delta S for the same dimension and same test condition. Hence YS is greater than YR. Question number 17. Two wires P and Q of same diameter are loaded as shown in the figure. Please see the figure. The upper end is fixed. P is m kgs and Q of same diameter, and the weight is 2 kgs as shown in the figure. Answer. Given LQ is equal to 2L. Two wires of P and Q diameter loaded in figure. The length of wire P is L meters and its Young's modulus is Y newtons per meter square, while length of wire Q is twice that of P and its material has Young's modulus half of P, and compute the ratio of their elongation. So we will first note down the given point. The length of Q is 2L and Young's modulus of Q is equal to Y by 2, where L is the length of P and Y is the Young's modulus of P. Therefore, Y is equal to F by A into delta L by capital L. That is simplifying, we get delta LP, that is change in length of wire P is given by 3mg divided by A into L by Y using the formula, standard formula. And similarly calculating for Q, wire Q, delta LQ is equal to 2mg divided by A into 2L by Y by 2, because here Young's modulus is half and length of the wire is twice L. So which we have put it here in the numerator as well as denominator. Simplifying, we get 8mg divided by A into L by Y. Hence, dividing equation 1 by 2, we get the ratio of delta LP divided by delta LQ is equal to 3 by 8. With this, we come to the end of chapter 9 on mechanical properties of solids. In the next chapter, that is in chapter number 10, we will study about mechanical properties of fluids. Till then, goodbye.